Hello there, welcome to this video, and this video is on mechanics. Okay, now we're going to take it very easily and very slowly. Okay, so we're going to look at some real basic stuff. So we're looking at a particle moving at constant velocity and in a straight line. Okay, so the particle, we're going to call the particle position. Now, we're going to call it S. Now, S is the distance from, I'm going to say the origin, but it doesn't have to be the origin, from some start point, from some point that we define, from a start point. Okay, so what do I mean by that? Well, let's draw a coordinate system. So we have a y-axis there, we've got an x-axis there. So this is y, this is x. 1, 2, 3, 4, 5. 1, 2, 3. Oh, let me do that again. That's awful. Where are we? It's not working. This is going to have to do it. No, for some reason it's not letting me get rid of those. Okay, so 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5, 6, 7, 8. Okay, now if S moved in the y direction, let's say it goes from here to here, we would say it's gone 5 meters. And if it moved in this direction, we'd say it went 6 meters. Okay, this is y is in meters and x is in meters. Okay, but particles don't move along the y and the x-axis. They move at sort of all points between, really, don't they? All right. So this is too ungeneral, if you like. It's too specific. So a particle will move somewhere in the middle. It will move like from here to here. Okay. Now this point here is defined as S. This is our position of the particle. Okay, now the position, it's not quite the position, it's the distance from the origin. Okay, so this point here is the distance. Obviously, it has a position as well. Okay, and the position in this case looks like it's 4, 3. In 4 along the x, 3 up the y. Okay, but S is the distance from the origin here. Okay, we can also have another S. Let's call this, put it up here for fun. Let's call this S2, and obviously it's further away, okay, but it's still the distance from some point, okay, so that's S. The S is equivalent to the distance, okay, from some point, okay, all right, there we go. Now, and that's what we call it S. We don't call it X or Y, we call it S because it's a combination of X and Y. All right, now let's have a look. Let's have a look at a simple system. And we're going to have a particle moving at constant velocity in a straight line. Okay, so let's have a look. Particle goes from S1 and it moves to S2. And its time taken, let's say, is equal to t seconds. Okay, so we can plot this, all right, on our coordinate system. There we are, there's the x, sorry, the y and the x. Okay, so now in this case, in this time, the S is the distance from the origin, okay, against time. Right, let's say it starts here, and this is S1, and it ends up here, and let's call this S2. So it's gone that distance. Okay, it starts off at this distance from the origin. Okay, and it ends up at whatever this distance is. Oh, that's awful, isn't it? Let me get rid of that. My undo's not working for some reason. All right, now it ends up this distance, and that distance from the origin, which is this. Okay, so it's moved away from the origin in some way. All right. Now, as we all know, the speed, or S, the speed, sorry, that's not right, is it at all? The velocity here is equal to the distance traveled divided by the time taken. Okay, so we can say V is equal to the change in S, okay, divided by the change in time. All right, now the change in S is, let me try and draw this distance. That's the change in S. This is delta S. And the change in time is this distance, delta T. Okay, so as you can see, let me draw it a bit in a different color. This color, let me draw a line there. Whoops, daisy, that's weird. And there. So this distance is delta S, and this distance is delta T. Okay, and as you can see, the gradient of this, or tan theta, which is the gradient, is delta S over delta T, which is going to give us the velocity. So in sort of Form 5 language, I guess you could say this is a distance time graph. Okay, and the gradient of the distance time graph, gradient, oh, that's not good, is it? Is equal to the velocity. Okay, but we've looked at it a bit more sort of deeply here, I guess. So the velocity is just change in distance over change in time. Okay. All right, so it's positional of S1 to S2, and that's the speed, isn't it, or the velocity? Okay, it's the ratio of those two. Okay, now we can extend this idea a little bit, and we can say, well, the velocity, you've just said, is the position of the final position, which is the change, isn't it? S final position minus the original position of S divided by the time taken, T. Okay, so where S is the final position, SF is the final position, SI is the initial position. All right, and obviously delta S, the change, is always the final minus the initial. It's always that. Okay, well, in this case, it's SF minus SI. Okay, and that's the change in position. Okay, delta S. All right, if we expand this, we get VT, and that times that, VT is equal to the SF, S initial, plus VT. Okay, so what does that mean? That looks, I hope you get the math. I've just cross multiplied and made the final position the subject of the formula. All right, so the final position is equal to the initial position okay, plus how far it's moved, obviously. How far, which is the velocity times the time it has moved, which is common sense, really, isn't it? All right, it's gone, it started off somewhere, it moved, and then we ended up where it is. Okay, but this is quite a useful equation, and I'll show you where we can use this nice equation. Okay, so let me go and copy something. I'm going to pause the video very briefly, if I can. I don't seem to be able to. Where can I pause you? Hold on. Oh, I won't pause it because I can't figure out how to pause this one. This is a bit weird, this computer. Okay, so we're going to have a look at a nice example here. Okay, here we go. And let me paste it here. And that's not good at all. So let me change this to 100. Okay, and find this awfully big thing here. All right, let's go. Gosh, it's enormous, isn't it? I don't know why it makes it so big. Okay, let's work out this using our nice new equation that we've just defined. All right, so two cyclists, A and B, start moving at the same time. The initial position of A is 0. That's S, all right, and the velocity is 20 kilometers a second, an hour. And the initial position of B is 150 kilometers, and he cycles at a velocity of minus 30 kilometers an hour. Determine the time position at where they meet. So let's have a look at A. A, this person, all right, starts off here, okay? And this is defined as our start point. So this is S, S-I for person A. And person A is going this way, let's say. All right, at a velocity of 20 kilometers an hour. Person B is here. Now this distance, let me try and get a nice pen here. This distance from the start is 150 kilometers. This is 150 kilometers, and this is the starting position for person B. And it's 150 kilometers away from the start. Okay, but this person is going at minus 30. That means it's traveling in the opposite direction, minus 30 kilometers an hour in the other direction. Okay, and we know they're going to meet somewhere. Where are they going to meet? Okay, determine the time and position at which they meet. Okay, so let's have a look at that then. It's quite a nice start. So the position of A is given by the formula this. So the final position of A, this is person A, is equal to the initial position plus VT. So the initial position, or the distance, the initial distance from some point is 0 because they're at the point, plus 20 times the time. I don't know what the time is, where they're going to meet, all right? But for person B, okay, the final position is going to equal the initial position, which is 150, and it's going the other direction, so it's minus 30t. Now we want them to meet, so we want the final position of both of them to be somewhere in the middle here. So we can equate these two equations together, okay, and we get this. We get 20t is equal to 150 minus 30t. Okay, if you rearrange that, you get 50t is equal to 150, from which we get t is equal to 3 hours. Okay, so it will take them 3 hours. This one will go for 3 hours, and this one will go for 3 hours, and they'll meet somewhere in this region. Okay, so now we've got the time it's going to take. We can find out where they will meet. Okay, whoops, let me change that to a smaller one. Whoops, daisy. All right, let's put this at 100. Okay, so where are they going to meet? Well, I can substitute into either of them now. So let's have a look. Let's do it for A. Okay, the final position, or the final distance, is equal to 0 plus 20 times t, which is 60 kilometers. Okay, let's do it for B just to make sure. The final position is equal to the initial position minus 30t. Okay, 150 minus 30 times 3, which is 90, and that's 60 kilometers, isn't it? Okay, it doesn't mean, it means they'll be at this position. Okay, so there's 150. Let's go back up to the picture. So where is 60 kilometers? It doesn't mean person B has gone 60 kilometers. It means they will end up at 60 kilometers from the original place, okay, which is this. Okay, so person A will go 60 kilometers this way, all right, because they started at 0. Person B will actually go 90 kilometers this way. But the place they meet here, let me do a nice different color, is 60